In this video, we're going to take a look at the different patterns that are found in chemical reactions, and we're going to take a look at writing chemical equations. All chemical reactions, whether simple or complex, are going to follow the same basic pattern. On the left, a group of reactants will be those chemicals or compounds that actually react. Once the reaction happens, that we indicate with an arrow, we will produce something that we write on the right and call the products. It's important to note, unlike a math equation, products are not the same as reactants. We cannot use an equal sign. We're going to see plus signs in chemical equations, but they don't actually mean addition. We're using them in place of the word and. There are many other symbols that are used in chemical equations. We might have symbols like a triangle, which often indicates that heat is being added. You might see S, L's, and G's that indicate whether the substance was solid, liquid, or gas, or the symbol AQ, which stands for aqueous, meaning it was dissolved in water. For a complete list of these symbols, check your textbook on page 283. The law of conservation of matter says matter is never created or destroyed. So when a chemical reaction happens, nothing new is appearing and nothing old is disappearing. All we're doing is rearranging it. It's like playing with Lego. If I take 5 yellow and 5 red and 5 blue Lego blocks and build a house, and then you take those same blocks that I built the house with and rearrange them to build a rocket ship, well, my house and your rocket ship should weigh the same amount because they were made of exactly the same components. And the same is true in a chemical equation. We should have exactly the same amount of each type of atom before the reaction as after the reaction. Because of this, the law of conservation of mass should also hold true. We should have the exact same mass before the compounds react as we do after. When we go to balance an equation, we start by counting the number of atoms we have before the reaction, before the arrow, and after the reaction. In this case of hydrogen and oxygen reacting to produce water, I can see that we have 2 hydrogen atoms. We have 2 oxygen atoms before the reaction. After the reaction, we have 2 hydrogen atoms and we have 1 oxygen atom. If you do no longer remember the rules for counting atoms, please check my grade 10 video called Counting Atoms. Once we know whether or not we have the same amount of air each type of atom on either side, we have to try to figure out how to make them equal. In this case, my hydrogens are same, but I have 2 oxygens before and only 1 oxygen after. It appears as though oxygen has disappeared. So I now need to try to make them the same. We must remember we can never ever change the subscripts. I can't just add this little 2. That won't work. H2O is water. H2O2 is peroxide. You can drink water, that's quite fine, but if you try to drink peroxide, you'll find a very nasty little reaction happens. A common first aid treatment for dogs who have accidentally ingested a poison is to give them a small amount of peroxide. When it hits the stomach lining, it foams at an incredible rate and causes the dog to vomit. Obviously, it's not the same thing. Hydrogen and oxygen do not react together in this way to form peroxide. So by changing those little numbers, you're making an entirely different reaction, and that doesn't allow you to balance. What we do instead is apply multipliers. Multipliers are coefficients. They tell us how many groups we have. In this example, we can see that if we use 2 groups of those diatomic hydrogen molecules, 2 H2Os means 1 group, 2 groups. And 1 group of the oxygens, you'll get 2 groups of the water molecules. Again, we can see 1, 2 groups. Taking a look at the balancing here, I can easily count 4 hydrogens before the arrow, 4 hydrogens after the arrow. I can see 2 oxygens before and 2 oxygens after. This is a balanced reaction. These coefficients that we see here act as a multiplier. Now, I don't see a number in front of the oxygen because we rarely write the number 1 in chemistry. But by default, we would assume if no coefficient exists that we assume there's at least 1. When I say they're a multiplier, it means that I've got 2 groups of 2, or 2 times 2 equals 4 hydrogens. 1 group of 2, 1 times 2 equals 2 of the oxygens. 2 groups of 2 equals 4 of the hydrogens, and because there's no number here after the oxygen, we again assume it's a 1. 2 groups of 1 equals 2 of the oxygens. In this case, we're noticing that the equation is balanced. We can use applying multipliers to try to balance all kinds of reactions. For example, nitrogen plus hydrogen makes ammonia. Both nitrogen and hydrogen are diatomic molecules and so have to come with a little 2 after them when they're in their pure form. NH3 is commonly called by its common name ammonia. When we start and check, I notice that there are 2 nitrogens before the arrow, but only 1 after. There are 2 hydrogens before the arrow and 3 after. In no way does this balance. There are several strategies you can use to balance the reaction. How can I make 2 nitrogens here into 2 nitrogens there? What can I multiply this group of 1 by? Well, the answer is 2. Putting a large number 2 in front of the nitrogen means that I now have 2 groups of nitrogens, and the nitrogens balance. However, this 2 applies to the entire species that it is before. So it also means 2 of these groups of 3 hydrogens. 2 times 3 is 6 hydrogens. At this moment, there's only 2. What can I multiply it by in order to make a 6? I can put a 3. 3 groups of 2 make 6 hydrogens, and this equation is balanced. You could also consider it in terms of pictures. I see a nitrogen, a hydrogen, and an ammonia. The nitrogen is made with 2 N's. The hydrogen is made with 2 H's. And the ammonia is made with 1 N and 3 of the H's. I put these into circles to remind myself that these are groupings that cannot change. When I look at this picture, I can see that this side here needs another red hydrogen. Another red nitrogen. How do I get another red nitrogen? Adding another group of NH3s allows me to have 2 nitrogens on the after side. However, now I see several of the green hydrogens and none on the before side. I must add more groups that look exactly like the one above it. Adding 2 more groups of pairs of hydrogens allows the amount of hydrogens before and after to be the same. Again, using this visual technique, you will notice that I required 1 of these nitrogen groups, and you see I've used 1 here. I've required 3 of these hydrogen groups, and I've required 2 of the ammonia groups to have the same amount of each type of atom before and after. Oftentimes, equations are given to us in their word form. When they're given to us in their word form, before we can balance it, we must first figure out all of the formulas and write them as a skeleton equation. I find that students quite often try to balance as they write, and you can't do that. You must first do every single crisscross and figure out what the formulas are going to be. Hydrogen chloride is made from hydrogen, which we know has a charge of +1, and chlorine, which we know has a charge of -1. When we do the crisscross, we get HCl. Hydrogen sulfate is made from hydrogen with a charge of +1, and the sulfate group, which has a charge of -2. Crisscrossing this gives H2SO4. Barium sulfate. Barium, with its charge of +2, reacts with sulfate with its charge of -2. We get Ba2SO4 2, which reduces to BaSO4. Remember always to reduce for ionic substances. Barium chloride, barium +2 and chloride -1, forms the molecule BaCl2. Now that you know the formulas, we can use these formulas to write the actual equation. Barium chloride, we said, was BaCl2. We're told that in this equation it will be aqueous. That means we have to dissolve it in water in order to make it react. Reacts with is shortened by the symbol plus. It's not the mathematical meaning of the word plus. It just means that we're putting it together with something. It's reacting with aqueous hydrogen sulfate. We figured out the formula for hydrogen sulfate is H2SO4. The AQ means that it will also have to be dissolved in water. It's reacting to produce. When we try to figure out what something's going to make, we draw an arrow. I'm going to apologize for staggering this, but I can only fit this big ink so closely on a page. It's forming a precipitate of barium sulfate. We figured out the formula for barium sulfates to be BaSO4. The fact that it's a precipitate uses the formula or the prefix PPT. You could also use a downward pointing arrow because chemists have shorthand for their shorthand. A precipitate is that white chunky stuff that falls to the bottom of the test tube. Well, in fairness, it's not always white, but precipitates are solids that are produced in chemical reactions. It's also going to form aqueous hydrogen chloride. So, and aqueous hydrogen chloride, we figured out the formula for hydrogen chloride, and we now know the symbol for aqueous. So here's my skeleton equation. In order to balance this equation, I need to find the multipliers to make the amounts equal before the arrow and after the arrow. The only things I'm trying to balance are the letters that you see before you in blue. The terms for aqueous and precipitate, those terms are there only to tell you about the physical state that the atoms or molecules were in when they reacted. Paying attention to what was happening, I see one barium before and one barium after. So far, so good. I see two chlorines before and one after. I fix this by multiplying the species by 2. This means 2 chlorines, but it also means 2 of the hydrogens. Checking before the arrow, I see 2 hydrogens. So far, so good. I also notice that there's sulfurs and oxygens. A little balancing trick is if you see a polyatomic ion and it stays in its same format both before and after. So in this case, we see that the SO4 group stays as an SO4 group. Then it's easier often to balance them as a whole group. There's one SO4 group before and one SO4 group after. This equation is now balanced. Balancing equations is a skill that you first learned in grade 10, but it is one of the fundamental skills required in chemistry. And as such, it's important that you practice it and become good at it. There are 4 questions in your textbook on pages 288 as a quick check for understanding. Then in your workbook, there are plenty of practice with balancing equations and going from word equations to balanced equations that you can find on pages 6, 7, and 8. In our next lesson, we're going to take a look at the different types of reactions and ways that we can predict the products for these main types of reactions.